Dear students, Quash's theorem is one of the very important theorems in complex analysis. Statement of this theorem is, if fz is analytic in a simply connected domain D and C is any closed continuous rectifiable curve in D, then integral over C fz dz is 0. Means if we have a domain D and if inside domain D we have a closed contour C which is rectifiable and continuous and also closed, then integral over C fz dz is 0. Now, corollary 1 of this theorem is for simply connected domains. Suppose fz is analytic in a simply connected domain D, then the integral along any rectifiable curve in D joining any two given points of D is the same. That is, it does not depend upon the curve joining the 2 points. Means if we have a domain D and inside the domain D we have 2 points, say one point is A, another point is B, and suppose we join these 2 points A and B by 2 curves, say one is C1, another contour is C2, then we have to show that integral over C fz dz is same as integral over C2 fz dz. Suppose the 2 points A represented by this complex number and B represented by Z2 of the simply connected domain D are joined by the curves C1 and C2. So, therefore, by Quash's theorem, integral over A P B Q A fz dz is 0 because it is a closed contour. So, therefore, A P B Q A fz dz is 0. Break into 2 parts, integral over A P B and then integral over B Q A fz dz is equal to 0. Now, integral over B Q A can be written as minus of integral over A Q B by using one of the properties of complex integrals which I had stated earlier. So, we have integral over A P B fz dz minus integral over A Q B fz dz is equal to 0. Now, what is A P B? A P B is the contour C1 and what is A Q B? A Q B is the contour C2. So, therefore, we have integral over C1 fz dz minus integral over C2 fz dz is equal to 0. That means, integral over C1 fz dz is same as integral over C2 fz dz. So, this is the Quash's theorem for simply connected domains. Now, let us come to Quash's theorem for multiply connected domains. So, what is this state? This states that if a closed contour C1 contains another closed contour C2, means this is one closed contour C1 and inside C1 we have another closed contour C2, direction is same as C1. And suppose that fz is analytic at every point lying in the ring shaped domain bounded by C1 and C2, means fz is analytic in this region, then we have to show that integral over C1 fz dz is same as integral over C2 fz dz. Now, this is a multiply connected domain. So, to convert it into simply connected domain, we make a cut from A to P. So, connect the outer contour C1 to the inner contour C2 by making a narrow cross cut joining a point A on C1. So, we take point A on C1 to a point P on C2. Okay. Now, if you open it up, we have that A, B, C, D, A, then go from A to P and then go from P to Q, this way, P, Q, R, P, A. So, then this is a simply connected domain. So, therefore, fz is analytic in this domain and is continuous on its boundary. Therefore, by Quash's theorem we have integral over a b c d a p q r p a f z d z is 0. Now, break this into 4 parts. Firstly, a b c d a f z d z plus integral f z d z on a p plus integral over a p f z d z, and then integral over p q r p f z d z, p q r p f z d z, and then plus integral over p a f z d z is equal to 0. Now, integral over a p and integral over p a will cancel out, because integral over p a f z d z is equal to minus of integral over a p f z dz. So, these two will cancel out, and we are left with integral over a b c d a f z dz plus integral over p q r p f z dz is equal to 0. Now, this can be written as, take minus sign here, then we have integral over p r q p f z dz, right. So, overall we have integral over a b c d a f z dz minus integral over p r q p f z dz is equal to 0. Now, what is a b c d a? A b c d a is c1. So, integral over c1 f z dz. What is p r q p? P r q p is c2. So, we have integral over c1 f z dz minus integral over c2 f z dz is equal to 0. Therefore, integral over c1 f z dz is same as integral over c2 f z dz. So, this is Quash's theorem for multiply connected domains, that if f z is analytic within this region, then integral over c1 f z dz is same as integral over c2 f z dz. This can be generalized. So, what is that result? The result is that if the contour C contains non-intersecting contour C1, C2, Cn, then integral over C f z dz is integral over C1 f z dz plus integral over C2 f z dz and so on, plus integral over Cn f z dz. Let's take 2 examples. Evaluate integral over c dz upon z minus 5, where c is mod of z is equal to 3. Now, what is mod z is equal to 3 represent? Mod z is equal to 3 represents a circle having center at 0, 0 and radius 3. That means, circle will pass through the point 3, 0 and minus 3, 0. Now, if we see this function, this integral over c dz upon z minus 5, if we take f z as 1 upon z minus 5, now 1 upon z minus 5 is not analytic at the point z is equal to 5, z is equal to 5 means at the point 5, 0, and this point is outside this circle. So, therefore, inside this circle f of z is analytic at every point. So, therefore, by Quash's theorem we have integral over c f z dz is equal to 0. That means, integral over c 1 upon z minus 5 dz is equal to 0. Let us take one more example of this type. Evaluate integral over c 1 upon z minus 1 dz, where c is the region mod of z less than 1. Okay. Now, suppose that mod of z is equal to r with the circle C, where r is strictly less than 1. Then you can see that f of z is 1 upon z minus 1, which is not analytic at z is equal to 1, but otherwise it is analytic at every point. So, therefore, f of z is equal to 1 upon z minus 1 is analytic inside and on C. C is the region mod of z less than 1. So, therefore, by Quash's theorem, integral over C 1 upon z minus 1 dz is equal to 0. Now, let us come to a very important result known as Quash's integral formula. If f of z is analytic within and on a closed contour C, so the function is analytic within and on this closed contour C, and if a is any point within C, a is any point within C, then value of the function at the point a is given by 1 upon 2 pi I integral over c f z dz upon z minus A. So, how to prove this? What we do is we describe a circle gamma about the center z is equal to a or small radius r such that please cancel one r here, small radius r such that this circle does not intersect the curve C. So, around point A we draw a circle gamma with very small radius such that this circle does not intersect C. Now, the function fz upon z minus a is analytic in the annulus bounded by C and gamma. So, fz upon z minus a analytic in this region. Fz upon z minus a is not analytic at z is equal to a, but z is equal to a is inside gamma. So, therefore, fz upon z minus a is analytic in this annulus region. So, therefore, by corollary to Quash's theorem, we have integral over C fz upon z minus a dz is equal to integral over gamma fz upon z minus a dz. Now, subtract fa from here and then add. So, we have integral over C fz dz upon z minus a is equal to integral over gamma fz minus fa upon z minus a dz plus integral over gamma fa upon z minus a dz. Now, since fz is analytic within C, it is given to us. So, therefore, f of z is differentiable, and if a function is differentiable, then it is continuous. So, therefore, f of z is continuous at z is equal to a. Now, apply definition of continuity. So, therefore, given epsilon greater than 0, there exists delta greater than 0 such that mod of fz minus fa is less than epsilon whenever mod of z minus a is less than delta. So, we choose r less than delta, so that above condition is satisfied for all z on gamma. Now, gamma equation of gamma is mod of z minus a is equal to r. So, therefore, z minus a is equal to r into e to the power I theta. So, therefore, dz is I r e to the power I theta d theta. So, therefore, integral over gamma dz upon z minus a is equal to integral from limit 0 to 2 pi, in place of dz write I r e to the power I theta d theta, and in place of z minus a write r into e to the power I theta. So, this comes out to be 2 pi I. So, substitute this value in equation number 1. So, we have integral over C fz upon z minus a dz is equal to integral over gamma fz minus fa upon z minus a dz plus 2 pi I into fa. Bring 2 pi I into fa on the left hand side and take the modulus on both sides. So, we have mod of integral over C fz dz upon z minus a minus 2 pi I fa is equal to mod of integral over gamma fz minus fa upon z minus a dz. Now, make use of the inequality which we had stated earlier. This is less than or equal to integral over gamma mod of fz minus fa upon mod of z minus a into mod of dz. Now, mod of fz minus fa is less than epsilon, mod of z minus a is equal to r. So, therefore, we have this is less than integral over gamma epsilon upon r mod of dz, and we know that integral over gamma mod dz represents circumference of gamma, which is 2 pi r. So, therefore, this is equal to 2 pi epsilon. Since epsilon is arbitrarily small and positive, so therefore, making epsilon tending to 0, this expression inside the modular sign is equal to 0, means integral over C fz upon z minus a dz minus 2 pi a fa is equal to 0. Therefore, f of a is equal to 1 upon 2 pi I integral over C fz upon z minus a dz. Thank you so much.